Today I'm going to start the same logic families whatever we discussed in the last class. So what are the types of logic families we discussed? Mainly there are two types of logic families. One is the bipolar and another one is the unipolar, based on what type of equipment or elements we are using in that corresponding logic family. Based on that, we are dividing into two categories. One is the bipolar and second one is the unipolar. And if you are considering the bipolar logic family, mainly again we are dividing that into two types. One is the saturated and another one is the unsaturated. How we are going to consider the region and in the corresponding transistor. For example, if you are taking the any BJT transistor, mainly we are having three regions. One is saturated, another one is cutoff region, and third one is the active region. And if any of the transistor is operated in the saturation region, then we can call this one as a saturated type of logic families. And if you are not using in the saturation region, then we are considering that one as a unsaturated logic family. Okay, so before going to discuss about the types of logic families, mainly we are going to consider the characteristics of logic families. That is, first one is the speed of operation. So this speed of operation is mainly calculated based on at what time we are applying the input and at what time we are getting the output. The difference between those two is considered as the speed of operation. And practically, if you want to calculate this propagation delay or the speed of propagation or speed of operation, just what we are going to do is you need to calculate two time periods or two propagation delays. One is when we are getting the propagation delay if the output voltage is varies from high to low, and second one is the propagation delay when the output voltage is going from low to high, and the average value of these two is considered as the speed of operation. Next we are going to consider the power dissipation, and this power dissipation is calculated as product of collector current with the supply voltage which we are applying to the corresponding circuit, and the product of these two is considered as the propagation delay. And this collector current also, again here we are calculated as average value of this collector current when the output voltage is at 0 and also output voltage is at 1. So the power dissipation is considered as VCC into IC. And if you just observe this power dissipation value, and if you are considering any type of circuit, if the power dissipation is low, means automatically from the device the heat is produced very less. If the heat is produced to high, means then what happens, the aging of that corresponding device is decreases. That is, for example, if the device is having more power dissipation, means automatically what happens is the lifespan of that corresponding device is reduces. That's why if you want to consider any type of circuit, always our main aim is to just take the less value of the power dissipation. So this power dissipation is calculated as VCC into IC, and this IC is totally depending upon the circuit what we are taking, but we can change this VCC value. Am I right or not? So nowadays the research is going on this type of circuit which we are going to take by considering the less value of this VCC. Previously we are using very VLSI circuits which contains 5 volts power supply. Now we are going to consider the research based on less value of this VCC. Okay, so like that, by reducing this VCC value, we can easily reduce the power dissipation. So due to that, for our electronics equipment, we can increase the lifespan of the corresponding circuit. Okay, so next, based on this power dissipation and the propagation delay, we are going to consider the figure of merit, and this figure of merit is calculated as product of power dissipation with the power. Okay, and always we are going to consider this propagation delay also as low as possible, and this power dissipation is also as low as possible. Due to that, if you want to measure the performance of any circuit, always we are going to consider the figure of merit value is as low as possible. So if we are going to choose any type of circuit for our applications, always we need to choose the low value of figure of merit for the corresponding circuit. Okay, so next we are going to consider the fourth type of characteristic is the fan in. That is, the corresponding gate or the circuit, how many inputs is capable of, that is the maximum number of inputs that can be applied to a logic gate is called as the fan in. And fan out is considered as how many number of outputs we can take it from the corresponding gate, that is how many number of loads we can consider. That is, if you are just considering the fan out of a particular circuit is 5, means from the corresponding gate we can apply maximum 5 inputs. After that, if you are going to consider more than that, automatically what happens is the performance of the driver circuit or the our logic gate is reduces. To avoid that, you have to choose the fan out, and based on the fan out only you just apply the loads. Next we are going to discuss about the noise margin. And when we are considering this noise margin, this noise margin is calculated as, for example, if you just consider 0, that 0 if you are going to apply, just I am assuming that I am going to apply either directly 0 volts is not possible. Sometimes we are going to fix the range for the input. That is, for example, if you just consider 0 volts to 2 volts, and if the range is between 0 volts to 2 volts, then we are going to consider that one as a logic 0. In the same way, for example, if you are taking the one, some 3.5 volts to 5 volts if you are applying, then we are going to assume that that is logic 1. So you can apply some 3.6 volts, or you can apply some 4 volts, or you can apply some 4.4 volts. Then the system or the device takes this one as a logic 1. Okay. And if you are applying the input as 0 to 2 volts, then we are going to consider that one as a logic 0. So based on these ranges, if you are going to draw the input range, then this is considered as VIL maximum. That is, if you are taking this VIL maximum, means the maximum voltage we are going to apply to consider this one as a logic 0. That is input low voltage maximum. Okay. So what is the input low voltage maximum with this requirement, which is 2 volts. Okay. Next, VIH minimum. That is, what is the minimum voltage we are going to apply, which is when the corresponding input is logic 1. So in our case, that value is equal to 3.5 volts. So now if you are just considering these things for the input case, then what happens? The output may be in the lesser range or in the higher range. That is, sometimes you will get low values or sometimes you will get high values. That is VOL maximum, that is output voltage maximum value, how much we are getting when the output value we are going to get it as logic 0. And in the same way, the output voltage minimum value, how we are getting when the output value is equal to logic 1. So these two ranges we are taking, and this noise margin is considered as the difference between these two. And if the noise margin is the value like this, that is, if you are just considering this as the noise margin when the logic 1 is there and when we are taking the logic 0. So this is considered as the noise margin. So why we are going to know about this noise margin is, in this noise margin also we can estimate whether the corresponding output is logic 0 or logic 1. Other than this, if you are just getting the values in between these two, then that is intermediate state, then we cannot estimate whether it is 0 or 1. So due to that, if the noise margin is very high, then automatically what happens, we can easily estimate whether the corresponding output is logic 0 or logic 1. So like that, you are going to consider the corresponding characteristics of a logic family based on the noise margin also. So if the output of the corresponding logic family is logic 0, then the noise margin VNL is calculated as this VIL maximum minus this VOL maximum. The difference between these two is considered as a low state noise margin. In the same way, high state noise margin is calculated as this VIH minimum to the difference between this VIH minimum to the VOH minimum. The difference between these two is considered as the high state noise margin. For example, if the noise margin is across up to this point, that is high, then what happens? We can easily estimate this range is considered as the logic 0 and this range is considered as the logic 1, and this is the intermediate state where we cannot estimate whether it is a logic 0 or logic 1. So if the noise margin is high, then automatically what happens is we can easily estimate whether that output is logic 0 or logic 1. That's why if you want to know about the performance of a logic family, always we need to choose the high value of the noise margin. Okay, so that is another characteristics of this logic family. Is there any doubts up to this? These are the characteristics of the logic families. Cheppamma.
ఒకసారి మళ్ళీ ఒక్కసారి బ్రీఫ్ గా చెప్పండి.
Okay. So the first characteristic is speed of operation. This speed of operation we are calculating based on the propagation delay, and this propagation delay is nothing but, for example, at 0 seconds time, if you are applying the input, at what time we are getting the output. The difference between those two is calculated as the propagation delay. Okay, so if you want to calculate this propagation delay, practically what we are doing is we are considering the average value of the propagation delay when the output voltage is going from high to low to the low to high. This high to low propagation delay is calculated as TPHL, which is the difference between 50% value of the input to the 50% value of the output. In the same way, TPLH means the difference between the output voltage when it is going from low to high. So based on this propagation delay, we have to estimate what is the speed of operation. If the propagation delay is high, means the speed is low. If the propagation delay is low, means the speed is high. So based on this propagation delay only, we are going to estimate this speed of operation. So next we are going to consider the power dissipation. So this power dissipation is considered as product of supply voltage into the collector current, and this collector current is calculated as average value of the collector current when we are getting the output value 0 and output value 1. So this is the amount of power dissipated when the corresponding circuit is in the operation state. Okay, and the product of this propagation delay and the power dissipation is called as the figure of merit. And if you want to choose any type of logic family, always we need to choose the logic family such that this figure of merit should be as low as possible. Next we are going to consider the fan-in. That is, the maximum number of inputs that can be applied to a logic gate is called as fan-in, and maximum number of outputs or loads we can take it for the logic gate is called as the fan out. Okay, this is the with respect to the input side, and this is with respect to the output side. Next, when we are going to consider the noise margin, this noise margin is calculated as difference between the corresponding two voltages when we are applying the, that is, maximum value of the input low to the maximum value of the output voltage when we are going to get the logic 0 as the output. In the same way, the difference between VIH minimum to the VOH minimum. This VIH is nothing but our input voltage, the minimum input voltage when we are applying the input as logic 1, and this VOH minimum is the minimum output voltage we are getting when the corresponding output we are getting as logic 1. These differences is called as the noise margin. And if you are going to consider this noise margin, this difference we can estimate what is the output, whether it is logic 0 or logic 1. In the intermediate state, we cannot estimate that whether it is logic 0 or logic 1. So if the noise margin is high, so automatically what happens is this intermediate state will be reduced. So when the intermediate state is reduced, automatically we can easily estimate what is the output, whether it is logic 0 or logic 1. That's why if you are going to consider the noise margin, The noise margin always you need to consider as high as possible. So propagation delay, power dissipation, and then figure of merit, these three characteristics should be as low as possible. Fan in, fan out, noise margin, these three characteristics should be as high as possible if you want to choose a better logic family or a better circuit. Okay, so these are the characteristics of the logic families. Next we are going to discuss about the types of logic families, and in these types of logic families mainly we are going to discuss about the saturated logic families. After getting this, we are going to discuss about the unipolar logic family, which is CMOS. Okay, so when we are considering this uh, saturated logic family, two things you need to remember when we are going to consider the saturated logic family, or otherwise if you are going to consider this one, what is that one is, for example, if you are going to consider the transistor T, if you just assume, or the transistor Q, and if this transistor Q should be, for example, if you are applying the base voltage is high, if you are applying base voltage is high, then what happens? The transistor goes to saturation region. When the transistor goes to the saturation region, then automatically we can say that the transistor T is in on state. So when the transistor T is in the on state, then it acts as a short circuit. Then it acts as a short circuit. So if we are applying the base voltage is high, automatically the transistor goes to the saturation region, and when it is in the saturation region, we are just identifying that it is in the on state. So when it is in the on state, it acts like a short circuit. Next, what is the next one is, when we are applying the base voltage is low, that is logic 0, then what happens is the transistor goes to the cutoff region. When the transistor goes to the cutoff region, we are going to consider this one as off state. So when it is in the off state, then it acts like a open circuit. The same thing is applicable for our diode also. When the diode voltage is, that is anode voltage is high compared to the cathode voltage, it is in the on state and it acts like a short circuit. When the anode voltage is low compared to the cathode voltage, that is, for example, if you are just considering the diode, so what is this? This is the anode and this is the cathode. So what is the characteristics of this diode? When this anode voltage is high, that is anode voltage is high, we are applying the input across this point, our anode voltage is high compared to cathode, then what happens is the diode is in which region? Forward biased or reverse biased? Diode is forward biased. So when the diode is in the forward biased, here just for easy sake, we are just assuming that it acts as a short circuit. It acts as a short circuit. In the same way, the reverse operation, if you are just considering, when the anode voltage is low, when we are going to compare with the cathode voltage, then what happens is the diode is in reverse bias. So when the diode is in the reverse bias, we are just assuming that, or we are just considering this one as a open circuit. Okay, so these things we are just assuming when we are going to consider the logic families types when we are taking in the saturation region. Okay, saturated types of logic families means you have to remember these things if you want to easily considering the characteristics or the operation of these logic families. What is the first one? When the transistor base voltage is high, then the transistor goes to the saturation region, and when it is in the saturation region, we are just considering it is in the on state and it acts like a short circuit. When the base voltage is low, then the transistor is in the cutoff region and it is in the off state and it acts like a open circuit. In the same way, if the anode voltage is high compared to the cathode, then the diode goes to the forward bias condition and it acts like a short circuit. And when the anode voltage is low compared to the cathode voltage, that is this value is low compared to this cathode voltage, then we are in the reverse biased and we are just considering this one as a open circuit condition. Okay, so these things when we are going to consider, then we can easily know about the operation of the circuit. Okay, so first we are going to consider the first type of logic family, which is resistor transistor logic. So here, by seeing the name only, we can easily estimate what are the components we are having in that logic family. So it is resistor transistor logic. So what is the meaning of this? It contains resistors and transistors are the major components. And when we are taking any type of logic family, always the logic family contains a basic gate. Okay, generally in most of the cases, you are going to choose the universal gate as the logic family. Why? Because if you are implementing one of the circuit, then it's enough to implement any one of the Boolean equation. For example, if you want to implement AND gate by using the RTL logic, then what happens? If you want to implement the Boolean equation, always you need to learn about the OR gate and also you need to learn about the NOT gate. If you know AND gate, OR gate and NOT gate, then only we can implement any type of Boolean equation by using this RTL logic. But if you are taking the universal gates, that is whether it is an AND gate or it is an OR gate, then what happens? If you know the NOR gate circuit by using this logic family, with this same circuit only we can implement any one of the Boolean equation. That's why most of the cases the logic family takes the basic gates as universal gates, whether it is a NOR gate or it is a NAND gate. But the basic gate for the RTL logic is NOR gate. So if you are taking this NOR gate, this is the circuit diagram of this NOR gate. And always remember that the NOR gate contains the transistors are in the parallel condition and we are applying the input signals through these resistors. That's why we are calling this one as a resistor transistor logic. And if you take these two are in parallel, so due to that it acts as a NOR gate. And how we are going to act this one as a NOR gate, I will explain you the operation. So if you are going to consider the first one, that is when we are applying the two inputs are low. Okay, so when the two inputs are low, that is for the Q1 and Q2 transistors, then what happens? Q1 is in the off state and Q2 is also in the off state. So when the Q1, Q2 both are in the off state, then what happens? Both are in the cutoff region. So when the both are in the cutoff region, I already explained, those two are acts as a open circuit. So when these two are acts as a open circuit, then what happens? This power supply is having a path only in this direction. So due to that, what happens? This total VCC goes to V0. Then the V0 value is equal to VCC, and this V0 value is high. So due to that, we can consider this one as a logic 1. In the same way, when we are going to consider the second case. So when we are considering the second case, that is we are applying the A value is logic 0 and B value is logic 1. So when the A value is logic 0, then what happens? The Q1 is in the cutoff region and B value is in logic 1, means Q2 transistor goes to the saturation region. So when the Q1 is in the cutoff region, it acts like a open circuit, and when Q2 is in the saturation region, it is in the saturation region, means it acts as a short circuit. So due to that, what happens? If you just considering this equivalent circuit diagram, here A across A, the Q1 transistor acts as a open circuit and the Q2 acts as a short circuit. And when we are applying any power supply, always it chooses the short circuit path. So this, there are two ways to go for this VCC, but it always chooses the short circuit path. So the VCC is directly goes to the ground, and there is no power supply goes to V0. So due to that, we can say that V0 value is equal to 0 volts, or we can consider this one as a logic 0. Or otherwise, in another way, how we are going to say this one is, one of the transistor is in the saturation region. So due to that, what happens, our output voltage is equal to, that is the collector current is very high. And what is the output we are going to consider here? How we are going to calculate the output voltage, which is nothing but the collector voltage? How we are calculating the collector current, collector voltage? VCC minus ICRC. Am I right or not? VCC minus ICRC. So when the transistor is in the saturation region, automatically what happens? This IC value is very high. So when this IC value is very high, VCC minus ICRC means this value becomes low, or this is considered as VCE sat. And this VCE sat, we know already that it is in between the range of some 0.3 volts to some 0.7 volts, like that, based on the type of diode which we are using for making this transistor. So this VCE sat is some 0.3 volts to 0.7 volts, means we can consider this one as a logic 0. Okay, so one of the transistor is in the saturation region, so it acts like a short circuit. So the power supply goes to the short circuit path, so there is no voltage goes to V0. So due to that, we can say that V0 is equal to logic 0, or some small voltage occurs across V0, so due to that, that is considered as a logic 0. So like that, across case 2, we are going to get output is equal to logic 0. Next, when we are going to consider the third case, across the third case, what happens? The same, A value 1 and B value 0. So here across A, we are getting the short circuit path, and across B, it is open circuit. Due to that also, there is no voltage coming across this V0. And again, this V0 is equal to VCC minus ICRC due to this transistor Q1, and output is equal to VC sat, or we can say that it is logic 0. Okay, and the fourth case, in this fourth case, what happens? A value 1 and B value 1. So both the transistors are in the saturation region, or in the on state, or in the short circuit condition. So when both are in the short circuit condition, we are getting two ways for the short circuit region. That's why here also there is no output voltage we are getting. So V0 is equal to 0. Now if you are observing the truth table, when A0, B0, our Q1 is in the off state and Q2 is also in the off state. That's why both are in the open circuit, means our VCC value is exactly equal to V0 is exactly equal to VCC. That's why it is logic 1. 0, 1 combination, that is any one is in the on state, means V0 is equal to 0. Now if you are observing this, only at 0, 0 condition, our output is equal to logic 1. For all the remaining cases, the output is equal to 0. So this is the truth table of the NOR gate. Due to that, we can say that this circuit acts as a NOR gate. This circuit acts as a NOR gate. Okay. So if you are taking this same circuit, when we are coming to the next class, draw these two transistor series is in series, and observe the corresponding truth table for the same operation. Okay. That is, you just draw the circuit diagram like this. Both these transistors are in series. So this emitter, we are going to connect it to the ground, and this is connected, shorted, and here through this resistor. Sorry. Here you just take the resistor, which is RC, and here you just apply the, that is, you just take the V0 voltage, and here you just apply VCC. Okay, and here through the resistors you just apply two inputs. One is A, another one is B. Okay, and this is RA and this is RB. Just note down this circuit diagram, all of you. And this is the transistor Q1 and this is the transistor Q2. And observe the what happens to Q1 and Q2, the same operation. When we are applying A0, B0, then what happens? Q1, Q2 both are in the off state, both are open circuit, and VCC is directly connected to V0, then output V0 is equal to logic 1. Like that, for the 4 combinations, you just observe what happens to our V0 voltage and identify that what type of logic gate it is. Okay, is there any doubts in this? We are having only 2 minutes left for our meeting class. Is there any
No,
doubts
ma'am.
remaining?
No, ma'am.
Is it easy? All of you note down the circuit diagram.
Ma'am.
ఈజీగా ఉందా అందరికి ఇది? టఫ్ గా అనిపిస్తుందా లాజిక్ ఫ్యామిలీస్?
ఈ పీడిఎఫ్ సెండ్ చేయండి మ్యామ్.
వీడియో సెండ్ చేస్తాను నాన్న. ప్లస్ ఆల్రెడీ మీకు పీడిఎఫ్ పంపించాను కదా, అదే పీడిఎఫ్ లో ఉంది ఇది కూడా. ఓకే, వీడియో పంపిస్తాను నేను. ఈ సర్క్యూట్ డయాగ్రామ్ నోట్ చేసుకోండి. ఓకే, శ్రీకాంత్
మ్యామ్ ఒకసారి కేస్ 2 ఎక్స్ప్లెయిన్ చేయండి.
నాన్న
కేస్ 2 ఒకసారి ఎక్స్ప్లెయిన్ చేయండి మ్యామ్.
నీ వాయిస్ బ్రేక్ అవుతుందన్న, నాకు వినిపించట్లేదు. జస్ట్ టైప్ ఇట్ ఇన్ ద చాట్ బాక్స్, అదర్వైజ్ టైప్ ఇట్ ఇన్ ద చాట్ బాక్స్. హర్ష కేస్ 2 ఎక్స్ప్లెయిన్ చేయాలా? ఓకే.